Okay, getting into 16.7 day 2, we're going to be looking at surface integrals in a slightly different way. Let's suppose that we've got a surface, it's an orientated surface, and we have a density, and we've got the rho function somehow defining that density. And what you're going to see is you have a velocity field. This is a vector field. And the rate of flow then, which would be mass per unit time per unit area, would be rho times v. So we have this vector function. And what I want to point out to you is, of course, the density would be mass per square unit of area. Okay, so what you're going to see as you're working this out is you might wonder what we could do with this new rho v. By the way, we could think of rho v as really our vector field in that regard. If we multiplied this rate of flow, by the dot product of the normal vector, and then multiply by the area patch, we would get a non-vector answer. Remember, with vector multiplication, the dot product would be the multiplication that leads to a scalar. So rho v, if we were to multiply that by really the most simple vector that we could come up with, that normal vector, and make it have a length of 1. And then if we were to multiply it by that little area patch, that resulting integral is going to be interpreted physically as the rate of flow through S. So that's really what we're coming up with right here. This rate of flow is what we're going to call flux. Okay, so the flux is a way to represent a rate of flow over that oriented surface. So what you're going to see is you've got some kind of a vector field defined. And like we said earlier, it's really thinking about that as a rate of flow, mass per unit time per unit area. But when we multiply by that dot product of the normal vector over this surface integral, that's how we find flux. So as we see here, definition 8 in that box says that the surface area of a vector field over S is equal to the surface integral of its normal component over S. And that normal component is very, very, very important. Now, when you're finding that normal component, I hope you remember that to find the normal vector, we would, just multiply by that cross product of RU cross RV. But if we wanted that to have a length of 1, we divide by that length. That's really what we're seeing right here. And that's, our N. So the next thing that you could very quickly pick up from the last couple of days is, of course, then you could say, now wait a minute, that surface integral was really evaluating that function over, that area, and that's really the area of the parallelogram there. You could see that these components cross out, and we can see then that the flux, that rate of flow over the surface, could really ultimately be found in a more simple way by taking that double integral of f dot RU cross RV and integrating over the appropriate parameter boundaries. So that's pretty cool. It's saying when the surface S is defined parametrically, of course. But this is what we call flux. So maybe the best thing that we could do is just, jump on in and take a look at a problem together. and try to work this thing out. Find the flux of the vector field that we have here. So F right there is that rho V, and they're just going to give that to you. And you've got a sphere that we have for this surface. So physically speaking, you've got this sphere, you've got this big ball, and let's just say that you've got this vector field that's going to help us find the rate of flow around that ball. So what we're going to do is ultimately just jump to what we see here highlighted. We're going to say, I need to define my surface parametrically. Wow, we do that so much. And when it comes to working with the sphere, guess what? We're going to go to spherical coordinates. We're going to go to spherical coordinates, guys. So what you want to do real quickly is remember that your x in spherical coordinates would be what? Yeah, we had rho, sine of phi, cosine of theta. But guess what your rho is for this sphere? It's just a 1. You could say rho is just going to be a 1. You could say your y is rho, sine of phi, sine of theta. So that can help you out. So ultimately, this is going to go by hopefully pretty quickly here. And then we could say, well, let's see, this is just going to be sine of phi, sine of theta. And then we could say our z is just going to be our rho cosine of phi. And if rho is just 1, we just have this thing right here. Well, here's the real cool thing. We could define that surface parametrically is saying we've got r defined as phi and theta. We could write this out in bracket notation. We could say, hey, that's just sine of phi, cosine of theta. Here we'd have sine of phi, sine of theta. And then for our z component, we've got the cosine of phi. So that's very, very important to get you started to finding flux. Why? Because what I've circled right here in blue writing, you got to have your surface defined parametrically. Well, as you're looking in yellow here, you're going to know that you're going to have to define your vector field parametrically as well. And they told you what F is, but we're also going to have a dot product with RU cross RV. So, what we're going to have to do is take our derivative of R with respect to phi. That's kind of like an RU. And let's think about that. What's our derivative with respect to phi? Derivative of sine of phi is cosine of phi, right? And then we go ahead and we take our derivative right here again. We get the cosine of phi times the sine of theta. Sine of theta is the constant. The derivative of the cosine of phi, though, is negative sine of phi. Look at that. Likewise, we're also supposed to take the derivative of r with respect to theta. And as we do that, we're coming back up here to our original form, but this time we take a derivative with respect to theta. Derivative of cosine of theta is negative sine theta, so we get negative. We still have that sine of phi as a constant. We go to our y component right here, the derivative of that with respect to theta. Derivative of sine of theta is cosine theta. So we've got the sine of phi times the cosine of theta. And then, this is the nice one. What's your k component's derivative? 0. Cosine of phi is a constant with respect to theta. And now we'd have to say, well, go ahead and take the cross product. Now, guys, this is where you want to use your 89. And I'm going to pause the video for a minute so that we can type this in. But maybe you'd like to have your phi as x and your theta as y. Okay, so let's do that. So we've typed this into the 89. Wherever we had a phi, we used x. Wherever we had a theta, we used y. And it's really just that exercise in patience. Hopefully you're feeling confident working, if you weren't here in class, on just being able to get that typed in. Still, all the same, you're not done when you get up to here, although you've made a giant leap forward. You really have. Remember what the flux ultimately is all about. Flux is going to be this double integral of a dot product, right? So we're going to come back up here and say our f, is, in fact, as we're looking at it, you can say your f is z, y, x. But we had parametric forms for z, y, and x. Z was the cosine of phi. We're going to have to apply those parametric relationships right there. Our y was the sine of phi, sine of theta. And our x, you can see on the screen right there, that's the sine of phi, cosine of theta. Okay? So at this point, what we're going to do is come back and realize that our flux was this double integral where we're going to have f dotted with that cross product that we just had come up with. And you can notice that that's dA and D, because as we're looking at that, we're going to say that the D is really the region that our parameters are going to be representing that surface. Okay? So, your F is this vector of cosine of phi, sine of phi, sine of theta, sine of phi, cosine of theta. But we're going to take a dot product of that. And the dot product that we're going to be working with is down here. It was that, cross product. Sine squared of phi, cosine of theta. Sine squared of phi, sine of theta. And then our last component, I think you can see right over here, is the sine of phi, cosine of phi. So we're getting there. And we're going to let the 89 finish this up for us in a moment. But first, working out our dot product. Remember, we're going to take our x components and multiply them together. So we would get cosine of phi, sine squared of phi, times the cosine of theta, plus, then we have to take our j components, or our y components, and multiply those together. We've got the sine of phi times the sine squared of phi. And by the way, I think I miscopied this other part right here. This was sine of theta, wasn't it? Okay, sine squared of phi times the sine of phi is sine cubed of phi. And then we'd have sine of theta times sine of theta. That would be sine squared of theta. Then we'd say plus, and then we're going to come over here. We can say, well, we're going to have a sine of phi squared, cosine of phi, and a cosine of theta. And of course, right here, if you're really on your toes, I think there are some like terms. These two together right here are actually like terms. So I'm going to really just get close to finishing this thing up. We're going to have a 2 cosine of phi, sine squared of phi, cosine of theta. Those two joined together. And here's your sine cubed of phi, sine squared of theta. And really our d phi and our d theta, we know that phi is going to span between 0 and pi. Theta is going to go between 0 and 2 pi. And we're going to let the calculator work it out. Via the calculator, you should get 4 pi over 3. You can confirm that on the 89.